This is the course Mechanical Vibrations. In this presentation, we will talk about transient response of general non-periodic forces using the Laplace Transform method. My name is Carmen Muller-Karger, and this corresponds to the content of Chapter 4, textbook Mechanical Vibrations from Brown. The Laplace Transform method can be used to find the response of any system under any type of excitation, including the harmonic and periodic type. The major advantage of methods is that it takes into account the initial conditions automatically. The definition of the Laplace transform is the integral from 0 to infinity of the function that we want to transform times e to the negative st dt. The steps of applying the Laplace transforms are the following. We will write the equation of motion of the system. We are very comfortable with the equation. We have mass times acceleration plus damper constant times velocity plus constant of the spring times displacement is equals to the applied force. We have to apply the Laplace transform to both sides of the equation. In order to apply the Laplace transform for a time derivative, we need the initial conditions. Once we have the Laplace transform, we solve for the variable that we want to solve. So in this case is x. We have here x in terms of time, and here we have x in terms of s. This is our equation. And now in order to obtain again x in terms of time, which is the solution of our differential equation, we apply the inverse Laplace transform, so that we were able to convert a differential equation in an algebraic equation, and applying the inverse Laplace transform, we were able to find the solution of this differential equation in the time domain. We will talk about transient and steady-state responses. The initial value of a response is when time is equals to 0. If we are in the Laplace domain, that means when s goes to infinity and is delimited when s goes to infinity of s x dx. The steady-state response in the time domain is when time goes to infinity. In the Laplace domain is s goes to 0 and is the limit when s goes to 0 from s x dx. This first equation is what is called the initial value theorem, and this last equation right here is what is called the final value theorem. The first equation that we'll be applying the Laplace transform is for a unit impulse function. We will describe this force or this function using the delta Dirac function, which means that it will be 0 for all times except for t equals to 0, where the impulse is applied, and for that time the value of the function is infinite. The Laplace transform for an unit impulse function, when we apply the integral from 0 to infinity, but all the values are 0, but for time very close to 0, so for a epsilon before time equals 0 and for an epsilon after time equals to 0. When we integrate that expression, it gives us that the Laplace transform for a unit impulse function is equals to 1. This 1 comes from e to negative s to 0, because the function is 0 for all time, but that small epsilon, where the impulse occurs. When we have a delay impulse that occurs at capital T, we can write the function so that is function t minus t, nothing occurs before t, and then we have the delta Dirac. 0 for all times different from capital T, and infinite when we got t at capital T. The Laplace transform then will be equals to from 0 to infinity, but the function is 0 for all times, but for an epsilon before capital T and an epsilon after capital T. And as you see, this one right here becomes a constant for t, and then we can say that this here is equals to 1. Therefore, our Laplace transform for a delay impulse becomes e to the negative st. The next function we want to find the Laplace transform for is for the step function. The step function is defined as 0 for time less than 0 and for 1 for time greater than 0. When we apply the Laplace transform for this equation, is the integral from 0 to infinity of 1, which is the value of the function, e to the negative st. We integrate this expression and they evaluate it in 0 infinity. When we evaluate infinity, this becomes a 0, and then when we evaluate in 0, that becomes a 1. Therefore, the Laplace transform for a step function is 1 over s. In the case that we have a delay step function, then we have 0 for t less than capital T and 1 for t greater than t. And when we evaluate this expression, then our limits of integration become from t to infinity. The integral is very similar, but they change the limit of integration. And then we get that the Laplace transform for a delay step function is this one right here. E to the negative st, where the step function happened, over s. The next function we like to find the Laplace transform is the ramp function. So we have a unit ramp. It means that the slope is equals to 1, and then our function will be equals to t for t greater than 0 and 0 for t less than 0. If we apply our transform, we have two functions that are function of time. Therefore, we have to apply integration by parts. If we have that the definition of integration by part is u dv equals uv, and the limits of integration minus 0 to t, the integral, v du. So let's name one of our functions u and one of our functions v. If we name u, for example, t, and the dv, we name it e to the negative s dt, then du will be dt, and v will be the integral of this expression. We introduce our values here in the integration by parts, and then we get the results. Therefore, the integral of this expression evaluated at between 0 and infinity is equals to 1 over s squared. Therefore, the Laplace transform for a ramp function is 1 over s squared. Again, if we apply the ramp function for a delay time, for example, capital T, we apply exactly the same procedure, but now we will have that the limits of integration change. Instead of being from 0 to infinity, it will be from t, where the function starts, to infinity. And therefore, we get our Laplace transform for a delay ramp that happens at capital T will be equals to e to the negative st divided by s squared. We did the Laplace transform for a unit impulse force, we did it for a step force, and we did it for a ramp. Now that we have other functions that are interesting for us and for our analysis in vibration, but I will not do it. Just look at the tables that you can find, and if we do the integral to apply the Laplace transform for a sine function, this is the result that we get. So the Laplace transform of a sine function is this one right here. The Laplace transform for a cosine function is this one right here. The Laplace transform from a exponential is this one right here. And if we have an exponential multiplied by a sine function, we get this one right here. And an exponential times the cosine function, we get this one right here. All those functions we will use to transform our differential equation and to apply the inverse transform to get our response in the time domain. Important too that we have to apply the Laplace transform for a derivative function, we will apply it to our acceleration, which is the second derivative respect to time, and the first derivative, which is the velocity. As you see, we'll need the initial conditions of that function. In our case, will be the initial displacement and the initial velocity to be able to apply the Laplace transform to the velocity and to the acceleration. Now that we have reviewed the Laplace transform, let's apply our Laplace transform to our equation of motion of the system, and we will convert this differential equation into an algebraic equation. We will apply the Laplace transform to both sides of the equation. In this side, you see that we have the acceleration. We already reviewed how to apply Laplace transform to a derivative. We have the velocity and we have the displacement. And this side of the equation, we already also review how to apply the Laplace transform to different functions. For example, a impulse force, a step function, or a ramp function, or if a sine function or an exponential function. We apply the Laplace transform from each of our components, and you see that the Laplace transform of a sum of function is the same as the sum of the Laplace transform of each of the terms. Here the mass is a constant, therefore we can take it out of the transform, and this is the expression to transform a derivative. We get s squared, the derivative of x, minus s, the value of the function at 0, in this case is the displacement, minus the initial value for the first derivative, in this case is the velocity. The second term is c times the Laplace transform of the first derivative. That will be s xs minus the function evaluated at 0. In our case, is the displacement. And then we have k times x, the Laplace transform of x, and then we have the Laplace transform of our function. Let's reorder our equation and put all the function in terms of s together. We put the terms that involve the displacement together, and we put the terms that include the initial velocity together, equals to the transform of our external force. Now we solve for xs, and we get that this is equals to fx, and we got the initial conditions, and we have to divide by this term over here. This is what is called the perturbation, because we have the external force and the initial conditions, and this is what is called the transfer function. As you see, the transfer function is a function of the properties of the system: mass, damping, and constant of the spring. And we can write the x dx as the perturbation function times the transfer function. As I said, the perturbation is a function of the external force and the initial conditions, and the transfer function is a function of the system characteristics. Let's talk about the transfer function, hs, for an underdamped system where zeta is greater than 0 and less than 1. We can write it in terms of our important parameters: natural frequency, damping ratio, and dampened frequency. We can convert c divided by m into 2 zeta omega n, and k over m is omega n squared. We can further manipulate this expression here by subtracting zeta omega n squared and adding zeta omega n squared, and we can write it in this form, which allow us to write the same transfer function in this matter. Why do we do that? Because that will help us to find the inverse Laplace transform. Let's find the response to initial conditions for a system that zeta is less than 1, an underdamped system. So we know that that will be this part of the perturbation, which is s m plus c times the initial displacement plus m times the initial velocity. All that multiplied by our transfer function. The transfer function, we already explained that we can write it in this way using zeta omega n and omega d. And in order to find terms that look like our functions from the table of Laplace transform, we manipulate that a little bit. Again, convert C over M in zeta omega n times the displacement, and this M here goes with that M. So we get these terms over here. Decompose this term and we will separate it in terms in the mean that is zeta omega n, and then we have another zeta omega n over here. So we decompose this fraction into fractions. Now this term over here is the same as this term, and this over here is the inverse transfer of a cosine. In order to transform the other fraction in an inverse, we multiply and divide by omega d, and then this and this is equal, so this is the inverse transfer of the sign. And here we have the inverse transfers of the sign. So looking at the Laplace transform table, we apply the inverse transform, and we see that this term over here will be, this is the inverse transform function. For this term over here, this is the inverse transform function. Remember that omega d is equals to omega n square root of 1 minus zeta squared, so omega n goes with the omega n. And then finally we have this term over here. The response to the initial condition is always the same, independently of the external force applied. And of course, this response for initial condition is valid for an underdamped system where zeta is less than 1 and greater than 0. Now, if we like to find the response of an impulse force using Laplace transform, we have this expression right here, which is the function of the impulse force, which is a delta de Dirac. We already know that the Laplace transform from that is 1, and then we have to find the inverse Laplace transform to find our response in time domain. We multiply and divide by omega d to have this term, and then we look into the table and we see that this over here is the inverse transform from the sine omega dt multiplied by e to the negative zeta omega n. And that's exactly equals to what we call H.D, which is the response to an unitary impulse force. Remember that we always have to add the response for the initial conditions. This response is for a system under damped system, which zeta is greater than 0 and less than 1. If we want to find the response for a step force, remember this is the function in the time domain, and if we apply the Laplace transform, we get that for a unitary step force is 1 over s. The response in the time domain will be the inverse Laplace transform of this perturbation function. We know that the Laplace transform for the step is 1 over s, so if we input right here, then we have to convert that into two fractions. To do that, where a, b, and c are unknown and we have to find it. Why do we have a only here and b, s plus c? Since we have here a polynomial of second degree, then the polynomial above is of first degree. To find a and b, I expand this expression right here and make it equal to that one right here. So the numerator has to be equals to 1, which is this one right here. And then making this a plus b equals to 0, a zeta omega n plus c equals to 0, and a omega n squared equals to 1, because in this polynomial we don't have terms to s squared and we don't have any terms multiplied by s. This is the only one that have a value that is 1. Then solving for a, b, and c, we get these values over here, and we will input these values into this fraction. This fraction over here is that one right here, and this one right here become that one, and I will separate this fraction into two separate fractions. So to get something similar to the Laplace transform, I will add and subtract this term. Here for that one I will multiply and divide by omega d. This one right here, we already know the inverse Laplace transform is 1. Then we finally found terms similar to the one in our table. Finally, we apply the inverse Laplace transform. This one here becomes k, because m times omega n squared is k, 1 over s, the inverse is 1. This term over here becomes e to the z omega nt cosine of omega dt, and this over here becomes this term over here. This is the response that we call g sub t, and it's the response for a unitary step force. And for the total response, remember that we always have to add the response for the initial conditions. To find the response or a ramp force is very similar to the procedure we applied to find the response for a unit impulse and for a step force. We first find the transform of our function. In this case is 1 over s squared. We plug it into our perturbation function that we found in the previous slides, and we have to apply the inverse transform to find x in the time domain. Here we have a polynomial of 4th degree in the denominator, so we have to decompose that a little bit, and we will convert into fractions. To do that, we have to find what are the coefficients a and b, c and d, and here we have a polynomial of 2nd degree, therefore we have a polynomial of 1st degree in the numerator, and as well here, right, we have a 1st degree polynomial. To find that, we just multiply these fractions and we make it equal to this one. So all this one here will become 1 when we find the numerator right here of these two fractions, if we find a common denominator for these fractions. And then this polynomial becomes 4 equations that allow us to find the 4 variables a, b, c, and d. Solving that 4 equations, we get those constants, and we include those constants into our function over here, and then we will be able to find the inverse Laplace transform. Here we have the 4 fractions, and then we have to manipulate all these fractions in order to find similar terms to our tables. If we do that, we find the inverse Laplace transform, and that will be equals to 1 over k. This term here becomes t, and this term here becomes 1 multiplied by 2 zeta omega n. This term here becomes a cosine of omega d multiplied by zeta e to the zeta omega nt, and this term here becomes a sine multiplied by e to the negative sine omega dt. And as before, we always have to add the response for initial conditions to have the total response of our system. Here we have a summary of the response to general forces using Laplace transform for a unit impulse, unit step, and unit ramp. You will notice that those are the same equations that we got using the convolution integral and the solution for the initial conditions for a underdamped system. And in this table you have the most common use Laplace transform for vibration purposes.